Okay, we should be recording, so welcome. Honors Physics, Chapter 13, Part 4. We're going to start on page 353, and we're going to be learning today pressure as a function of depth and what floats your boat. To start off with, we're going to try to come up with the equation highlighted here, pressure of water on a body. So, welcome again, pressure as a function of depth and what floats your boat. So, most of you have probably experienced at one point or another swimming underwater and noticed that the deeper underwater you go, the more your ears start to hurt. The reason for that is the deeper you go underwater, the greater the pressure. So the greater the pressure, the more it starts to squeeze in on your poor little eardrums. The reason you feel more pressure the deeper underwater you go is because of all of the water above you. The water above you has some weight, and that water's weight is bearing down on you. So if you have 10 kilograms of water above you, then you've got 10 kilograms of water bearing down on you. If you go deeper, you might have 10,000 kilograms of water above you, which would be unbearably pressurized, right? I mean, that would squeeze you terribly. So the deeper you go, the more pressure you're going to feel because there will be a larger weight of water above you. So let's try to draw a picture and apply some math to this and see what we can come up with. So let's see, there's the surface of the water. Here's you underwater. There's you underwater. You are a depth h below the surface, and your body has some cross-sectional area A, some surface area, okay? Above you is going to be all this water, okay? That water is going to have some volume. That volume of water would be your cross-sectional area times the depth h. That tells you the volume of water. It is the weight of that volume of water above you that is going to cause the difference in pressure. It is going to cause that pressure on you. So what is that going to look like? Well, we know pressure is force per area, and the force on you is going to be the weight of the water, right? The force on you is going to be the weight of the water above you. It is going to be the weight of that volume of water. Okay? Well, what is that weight of volume of water going to be? Well, we know that weight is mg. Awesome. We know what g is. What is the mass of all that water above you? Well, who knows? I don't know how deep I don't know how much water is above me. How do we know the mass? Well, let's see. We know that the density of water is 1,000 kilograms per cubic meter, so we can use the density. We know that density is mass per volume, so the mass of water would just be the density times the volume. And hey, I know what the volume is. The volume's right here. So I'm going to use that. The mass is the density times the volume, so the mass would be the density times the volume, which is A times H. So mass is density times volume, A times H. So the force is going to be the mass, density times volume, times G. Okay? Hold on, I gotta go let my dog out. I'll be right back. All right, I'm back. Sorry for the interruption. So the force that we're talking about, the weight of the water is mg. M is now density times volume, so there we go. And that means we can write the pressure now. Pressure, which is force per area, so force per area. And luck would have it, the areas cancel out and gives me rho hg for the pressure, which is the equation we tried to come up with. The pressure is going to be the density of the fluid, the depth of which you are in that fluid, and g. So density rho, h is depth, g is our 9.81. So from this equation you can see the deeper you go, the larger h becomes, the higher the pressure. So there we have it, pressure as a function of depth. Awesome. All right, the next thing to talk about then is buoyancy. Buoyancy. And I have such a hard time spelling buoyancy. Here we go. Buoyancy. Another word for buoyancy, what floats your boat? So, what floats your boat? Well, when you are submerged in a fluid, that fluid will exert a force on you, and that force will always be upwards. The upward force a fluid exerts on you is called the buoyant force. A fluid will exert an upward buoyant force on anything submerged within that fluid. The reason is that the deeper you are in a fluid, the greater the pressure. So if you imagine your body, say, oriented vertically underwater, your head is underwater, pointed towards the surface, your feet are pointed towards the bottom of the water, the bottom of the lake, whatever we're talking about, bottom of the pool. The pressure on your head will be smaller than the pressure on your feet because your feet are deeper. Because your feet are deeper and at higher pressure, there will be a greater force down there than there is at the top. So you're going to have a small force at the top, a large force at the bottom. Those add together to some net upward force. And that upward force is called the buoyant force. Now, right now you're thinking, what in the heck did you just say? Well, I'm going to draw it. So there's the surface of the water, and let's imagine for simplicity some cube, so the dimensions are easy. And that cube is going to be a depth h underwater, and that cube is going to be a cube whose sides are all length L. So cube length L sided and h depth. Well, there's going to be some force exerted by the fluid there, and there's going to be some force exerted by the fluid there. Right? Force at the top, force at the bottom. The force at the top is just going to be pressure 1 times area. The force at the bottom is going to be pressure 2 times area. And area is just going to be the area of a side, which would be length times length, right? Okay. The only other forces to think about are any forces in the horizontal direction. Well, forces in the horizontal direction, like the two I just drew, are at the same depth. So they're at the same pressure, so they'd be the same force. So a force going to the left and a force going to the right of the same amount would cancel. So forces that way and forces that way would all cancel. All that's left is the upward and downward force. And we know because force 2 is happening at a deeper depth, force 2 would be greater than force 1. So there will be some net upward force. That net upward force is called the buoyant force. The buoyant force that the fluid exerts is just the difference between the force at the bottom of the object and the force at the top of the object. Okay? So let's keep exploring. The buoyant force, therefore, is going to be the force at the bottom, so that's pressure 2 times area, minus the force at the top, pressure 1 times area. Well, what's pressure 2? Well, pressure 2, well, we know pressure is just going to be density, depth, and g. So what's pressure 2? Well, pressure 2 is going to be the density of the fluid times the depth. Down here, the depth is going to be, h plus L. So density going to be h plus L. That's the depth. And g, because it's g. And then now the area. Minus pressure 1 rather, which would be rho hg. This time we're only at a depth h, remember. Force 1 is only at a depth h. So gh and area. Cool. And we keep going. We should expand. We don't like big complicated terms, so that's going to be rho hga plus rho lga minus rho hga. That one and that one cancel, so that leaves us with rho gla. Well, volume is going to be that length times that area, so we can say that the buoyant force is going to be the density, g, and the volume. That gives us the buoyant force. The total upward force a fluid exerts on an object is just going to be the density of the fluid, g, and the volume of displaced fluid. What is the volume of displaced fluid? Well, if you submerge your entire body underwater, then the volume you have displaced is a volume equal to your own volume. Cool. Let's try a problem. Let's try example problem 3, if I can find it. Hey, there we go. On page 356, example problem 3. A cubic decimeter, what a strange word, a cube whose sides are 1 times 10 to the minus 3, a cube whose sides are such that the volume is 1 times 10 to the minus 3 cubic meters of granite is submerged in water. The density of the granite is 2.7 times 10 to the 3 kilograms per meter cubed. We want to figure out A, the buoyant force acting on that block because it's submerged in a fluid, and the apparent weight of the block. All right, so let's go to it. Example 3. All right, we are told the volume is 1 times 10 to the minus 3 cubic meters. We are told the density of granite is 2.7 times 10 to the 3 kilograms per meter cubed. And we want to know, question A, the buoyant force on this block of granite when it is submerged in water. So, buoyant force is density times volume times G. So let's see what that is. The buoyant force would be the density, the fluid that we're talking about, remember. We are not talking about the density of the block of wood. We are not of granite. We are not talking about that density right now. That is not the density we are talking about. The buoyant force is determined by the fluid, so it's going to be depending on the properties of the fluid. So the density here is going to be the density of the fluid, which is the density of water, which is 1,000. Okay, times the volume that's displaced. Well, the entire cube was underwater, so it would be its entire volume, and G is 9.81. So the buoyant force on our cube is 9.81 newtons. Hip hip hooray. Buoyant force on the cube, 9.81 newtons. Part B. That is the total upward force. Part B. They now want us to find the apparent weight. For lack of a better symbol, we'll just use that, apparent weight. Apparent weight is defined as the difference between your actual weight and the buoyant force. When you float in water, you feel weightless almost, right? You feel like you're a lot less, you weigh a lot less, right? You're being supported by the water. So you appear to weigh less. Your apparent weight is going to be your actual weight minus the buoyant force. So your apparent weight is your actual weight. So in this case, they're talking about the apparent weight of the block of granite. So mg, that's the weight of the granite, minus the buoyant force. The buoyant force we just determined. The problem is we don't know what the mass of that block of granite is. We don't know that. We were told the density of the granite, and we know that density is mass per volume. So the mass of that piece of granite would just be the density of that piece of granite times its volume. So the mass of that piece of granite would be 2.7 times 10 to the 3, the density of that piece of granite, times the volume of that piece of granite, which was 1 times 10 to the minus 3, which gives a mass of 2.7 kilograms. Now that I know the mass, I can continue on to find the apparent weight. The apparent weight is going to be mg minus the buoyant force. So that's going to be the mass, 2.7 kilograms, g, 9.81 meters per second squared, minus the buoyant force, which by fluke is 9.81 newtons. That gives us an apparent weight of 16.7 newtons. That block of granite appears to weigh 16.7 newtons because it is submerged in a fluid experiencing an upward buoyant force. Alrighty, that should end today's lesson. What I think you guys should work on to the best of your ability are the practice problems at the bottom of page 356, 27, 28, 29, 30, and 31. Have a go at those, and we will see you next time.